Are you willing to learn general theory of relativity? Are you excited to learn about this wonderful science? Do you feel at some point of time you lack the knowledge of this complex mathematics, of tensors and differential geometry, curvatures, complex equations? Don't worry, this video is just meant for you. In today's video, I'm going to explain everything about Einstein's general theory of relativity with a basic knowledge of mathematics. You will come across a fascinating history of scientists, mathematicians, friends who helped Einstein, and a lot more. You will know more than what others generally know about general relativity, yet you do not have to crack your head into these complex, difficult mathematics. How? Let us find it out. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to a simplified approach to general theory of relativity. Okay, so first what we are going to do is that we should first learn who should watch this video, because it is a simplified approach. Definitely this is not going to cover up the difficult, complex mathematical approach, but we should learn first that who can watch this video. So people who are physics enthusiasts who are willing to learn more about general relativity are meant for this video. A student of physics, yes, those who are willing to learn, the physics students can watch this. Thinking of taking GR as a special paper after doing your master's in physics, yes, you can do that. Thinking of specialization, yes, definitely. Those who are thinking to take general relativity and astrophysics, it is meant for that. People who are fascinated by general relativity, I mean to say, you really want to know, you are really fascinated by this wonderful subject, can watch this video. Non-specialist of GR who are not, I would say, not much into mathematics, but very much willing to learn, very much willing to know more about GR, yes, the video is meant for you. Non-mathematicians, in the sense that this video doesn't cover up too much of mathematics, and learners, knowledge seekers, and educationists, because general theory of relativity should be known for any physics or any graduate in order to be in the society and mark as a kind of a person who knows about general things. So definitely knowledge seekers and educationists. So these are the people who can watch this video, but it is not that it is strictly meant for that anybody can watch this video. Okay, so first what we are going to see is that there is an amazing fact about general theory of relativity which very few people know. We will first start our video by knowing this amazing fact. Now, it was the year 1915, and as you can see on the 4th, that is the Thursday, the first publication of Einstein's general theory of relativity happened. Then again it happened on 11th, that is on the general theory of relativity, which contained certain corrections which Einstein did. And then again it happened on 18th when he calculated the perihelion motion of Mercury from the earlier general theory of relativity. And lastly it happened on 25th, which is the final paper which contained Einstein's field equation. It is called the field equations of gravitation. So this is an amazing fact. At an interval of 7 days, everything happened on Thursday, 4th, 11th, 18th, and 25th. Let me know your views. Do you consider Thursday as a lucky day for you? So the first thing that we need to understand in general, very quickly, what is general theory of relativity? So we can see that this particular equation, which we are going to definitely see not on a mathematical basis but in a general basis, dictates the entire philosophy and understanding of general relativity. So this is an Einstein's field equations which contains 10 nonlinear partial differential equations in 4 independent variables. Also, it is something which relates the local space-time curvature with local energy, momentum, stress within that space-time. And Einstein field equation relate the space-time geometry to the distribution of mass, energy, momentum, and stress. And that is basically determined by what is called the metric tensor of space-time for a given arrangement of stress, energy, momentum in space-time. So more or less we can say that this is the central equation which guides general theory of relativity, and it contains of 10 nonlinear partial differential equations. It is something which is related to local space-time curvature, and the field equation also relates the space-time to the distribution of mass, energy, momentum, and it shows how gravity is caused by the curvature of space-time. Now you see in this particular equation there are certain things which emerge as very important. The first thing, why I am calling it equations instead of one equation, you can see, because the equation that you see is not one equation, but there are total around 16 partial non-linear differential equations. Out of that, 6 of them are common, and we are only dealing with 10 non-linear partial differential equations. When we talk non-linear, I'm trying to tell you that it is something which is not linear, that is not moving in a straight path. It takes certain changes, which we will see what it is. Also, what I meant to say, it deals heavily with the space-time curvature. That means it is considered space-time not as flat as Newtonian or Galilean physics did, but it is a curvature of space-time. And also it contains 4 independent variables. We will see what those independent variables are. So 1, 2, 3, 4, these are the 4 important, very important thing that emerges out of these equations. We are going to dissect, but on a very generic view, what those equations and what those things are about. Just a point of note that in case that you really want to explore much about those, go to my playlist on General Theory of Relativity. It contains a very detailed mathematical videos which explains each and everything. Okay. So we now know that what is general theory of relativity. First, we need to dive deep into understanding general relativity, but before that, we need to understand the precursor, or how the special theory of relativity really emerged, and then only we can understand what is general theory of relativity. Okay, so we turn the pages of history and go back something around Friday the 30th, not the 13th, fortunately, 1905. When this paper was published. Now, the Annus Mirabilis papers, Annus Mirabilis actually means that miracle year, are the 4 papers which Albert Einstein published in Annalen der Physik, which means Annals of Physics, a scientific journal. Now, these 4 equations or papers, I would say, were major contributions in the foundation of modern physics. The revolutionary sciences, I would say, understanding of the fundamental concept of space, time, and energy changed, because Einstein published these remarkable papers in one single year, 1905, and that is why it is called Annus Mirabilis, or miraculous year in English. Now, the first paper explained the photoelectric effect, which establishes energy of the light quanta by the equation E equal to hf, and was specific discovery mentioned in the citation of Einstein's work, and he won the Nobel Prize in Physics for that. The second paper explained what is called the Brownian motion, which established Einstein relation and led the then called reluctant physicists to accept the existence of atoms. The third paper, which introduced special theory of relativity, which established the universal constancy of the speed of light c, which is a constant for all reference frames, I would say a theory of space-time. And fourth paper was the mass energy equivalence on the theory of special relativity, expressed in the famous equation, as you see, equals to mc square, which actually led to the discovery and usage of atomic energy. All those papers combined changed our view of space-time, or I would say space-time as a whole, and we came to know something which you are going to discover. Okay, so the postulates of special relativity tells that the laws of physics are invariant. That means it won't change in all inertial frames of reference. Remember, we are dealing now with inertial frames of reference, that is frames of reference with no acceleration, and the speed of light in vacuum is the same for all observers, regardless where the observer is located. So this is a kind of a nice demonstration. So inertial frame of reference F equals to ma gets changed to F prime equals to ma, and these are Galilean's transformation which happens, and the acceleration here is the same in both frames. So we are dealing with the postulates of special relativity. That means what it assumes, that the inertial frame of reference and the speed of light in vacuum is same for all observers. Now, why it is called special? The reason is that it deals with certain conditions which are very restricted and which are very special. As you see here, I have just explained the age-old Newtonian concept that the apple is falling is based basically on the gravity as a force, which was later changed by Einstein as something which is not a force but a curvature. So Einstein's new apple inside here, you can see spaceship, famous experiment accelerating upwards, and the apparent path of photon, which appeared to be straight, now appears to be this one, which is a curved path. So it is called the Gedanken, or the thought experiment, famous, which Einstein did, and he came to the conclusion there is nothing called gravity as a fictitious force. Gravity and inertial forces are something which are indistinguishable. So this is again a story which goes when Einstein was working at his Bern office, and suddenly he felt that the floor is not there and he's falling down, so that falling and the person falling in free space, both of them are the same. So the question arises that, as you see, the apparent path of photon bends when the elevator or the spaceship accelerates. Question arises that what actually bends light, and the answer is that it is because of the space-time curvature. So we come to the principles or postulates of general relativity from special relativity, which says the principle of general covariance. It means that the laws of physics themselves should be independent of an observer's motion, and the equivalence principle, which says that the gravitational acceleration is the same for all observers in a gravitational field. Now this principle, that is the principle of covariance, as we will soon see, actually leads to something which are called tensors. Now why tensors come in, we will soon explain, but principle of general covariance is something we need to understand. And the equivalence principle actually gave us the result that gravity is not a force, it is a geometric property of space-time, and gravity is something which cannot be distinguished from acceleration. Now we would have to take a step forward and understand this very technical term, what is called covariance, because as the postulates of general relativity shows covariance, so a lot of physics and the entire future of our video depends on what is called the principle of general covariance. We will take a very simple approach, not going into mathematics. So here is a person who is throwing a ball right over here, and it is in one frame of reference. This same person is throwing a ball over here, but it is in a rotated axis, right? So what happens is that the event takes place here and the event takes place here, but the events will be measured in the same way in all frames of reference. That means the throwing of the ball, if it continues in one frame of reference and goes to the rotated axis, it will be measured in the same way. There won't be any change. Similarly, if this person is throwing the ball, and again the same person is throwing the ball, and it is an extended axis, that means I have expanded the x and y axis, and the event takes place in both these places, again it will be that the events will be measured in the same way in all frames of reference. So if I want to measure the sphere, for example, I want to measure this one, right, the big circle, and if I somehow blow the sphere in air and make it kind of an oblate spheroid, then what happens? This straight line elongates, right? It gets stretched. So what Einstein told is that the general laws of nature must be identical, must be expressed by identical equations relative to all other systems, whichever way they are moving. So this is the basic important thing, that wherever and whatever be the frame of reference, extended, rotated, stretched, but the general laws of nature must be expressed by identical equation. This is called the principle of general covariance. That means anything, if it varies, it will vary with something. That is why it is called co plus variance. That means varying with something. Now this covariance principle, how it takes place from a flat space-time to a curved space-time, because it has now moved from Newtonian physics to modern physics, that will be explained in the next part of the video. So now we are going to see that how we move from flat space to curved space and how it really changes the entire physics. I will take a nice and simple demonstration. If this is a flat space and we are measuring something, you can call it a vector or a line, depends upon this red axis which we called AY and this x-axis which is called AX. Then we measure this by these blue dotted lines. Now let us plot the same thing x and y on a curved space where the x prime and y prime, which is the curved axis, is something like this. And now we measure the same A, but you see that this part A prime x is extended, same is A prime y, which is extended. So what happens is that A prime x is longer and A prime y is also longer, but somehow A remains invariant. Remember, you can just flick back the video and you can see that we just talked that Einstein spoke that the laws of physics should be invariant. That means it won't change. But as you see that as we move from flat to curved space, things change. Now the question that arises is that how can we measure this change? We need to measure, but we need to make the main thing, that is the vector pointing towards A, to be invariant. And that is what is called the requirement of tensors. But before that, I would also like to give you another demonstration. So in Newtonian mechanics, space and time coordinates are independent. So if I move from x, y, z, that is, we have taken a space as a whole and time. In Newtonian time, we also require tensor, but that was a classical tensor. So here is a person who is throwing a ball and it arrives here, and we measure those points, this, and this. At every point, what we find is that these lines are orthogonal, right? But if we get a kind of a curved space and we draw those grids and we take those points, right? And when this person moves around this and this and this, so what we find is that you see these lines are non-orthogonal. That means it is not perpendicular to each other, and this is what is required in tensors, and it leads to many technical terms which we are ignoring in this video, like manifolds, tangent bundle, and tangent space. If you're really interested to know those technical terms, I have explained this in details into my playlist of General Theory of Relativity. You can go and check it out in Physics for Students. So that is why the tensors are required, because these changes need to be measured, yet the main vector has to be invariant. So the question is that the tensors in general relativity, how it measures the change from flat space to curved space. Now the origin of the word tensor is the Latin word tensor, which means generally to stretch. That is why it is related to something called muscles. So a muscle that tightens or stretches, but it describes linear relations on scalar vectors, matrices, and other algebraic operations. Okay, so we need to look a little bit into these people, the great people who contributed immensely in development of tensor. Augustin Louis Cauchy, who developed the Cauchy stress tensor. Then this gentleman, William Rowan Hamilton, is the first to coin the term tensor, and he used in quaternions. Then comes this person, we all know him, one of the greatest mathematicians, Bernhard Riemann. He used in measuring Riemann curvature tensor. And then we find Josiah Willard Gibbs in 1884, who used what is called an indeterminate product. Now remember, it was all during those times when tensor was not fully developed. These are the people and many others who contributed in developing tensors. Now here is somebody whom I would like to take a close observation. He was one of the closest friend and one of the greatest contributor of general theory of relativity. His name was Richard Grossman. Now Richard Grossman, this page actually shows that it was Grossman who introduced Einstein the Riemann tensor as a mathematical resource for general theory of relativity. And here you can see I marked it in red. This is Grossman's signature. So as we come into general theory of relativity, we have to remember that Einstein during that time was totally unaware about anything of an exotic object called tensor, and it was Grossman who first introduced this concept. Now there's a small story which says that after arriving in Zurich, Einstein and Grossman started a collaboration that would almost lead to the discovery of general theory of relativity, and that would in any case result in Grossman's most well-known scholarly achievement in 1956. So metric components as a tensor introduced to Riemann, a tensor to Einstein, and the general vector calculus, all these he was master. And there's a famous saying that Einstein approached Grossman for help, saying, Grossman, Grossman, you have to help me or else I will go crazy. So this was Marcel Grossman. We can even make a complete video because I have studied the Grossman's contribution to general theory of relativity is huge, it's immense, and it's very important. Because without Grossman, possibly Einstein wouldn't have got the knowledge of tensor calculus, and we would not have been discussing today about general relativity. So it was not only Grossman, it was these other friends like Michel Besso and Grossman, along with Einstein. Grossman introduced tensor algebra, Riemannian geometry, and so on. And these are the people who actually, contributed immensely to develop Einstein's general theory of relativity. Without them, it was not possible. So a kind of we should know that who are the people who really made this possible. Okay, so the development of tensor calculus actually started with these shapes. You see, these are very odd shapes. So study of curved surfaces. Then we see there is a sphere, and we divide further. And what we do is that we differentiate it. That is, we differentiate and make it smaller and smaller and smaller. Why? Because we can use calculus on it, right? Then we make it on a space-time manifold, and these space-time manifold again is done measurement of tensors, which are invariants, and it is a system with the laws of general covariance. It's a kind of a, I would say a flow chart where you can see that how from a study of curved surfaces we moved to differential manifold and how tensors came into being. Now, in this phase of the video, we should also take a step back into understanding another development which was doing parallelly with Einstein when he was developing the theory of relativity, a very important subject which later emerged to be one of the most important subject, and we got a lot of researchers going nowadays, and this is called differential geometry. And we are going to just look into this subject, what is differential geometry and why it marks so important in terms of contribution to general relativity. Okay, so what happens in differential geometry is that whenever we are measuring lines which are into, I would say, Rn, so you can say it is a real number of n dimensions. So whenever we do this, it gets a straight line. But when we take a kind of a curved surface like this, or we take a sphere where the curvatures are like this, then we need to differentiate those surfaces. That means divide into small parts so that we can apply calculus. And why do we use, when we do calculus, we see that the usual Euclidean geometry fails. That means the sum of the angles of a triangle on a sphere is not equal to 180 degrees, which is generally used. So we differentiate and further differentiate the structure in order to apply calculus. And when we apply calculus, we are seeing that the usual Euclidean geometry doesn't really work. So this is the contribution and application of differential geometry. So this is actually technically called manifold. So we call a manifold offers the most general setting where we can use calculus. A simple illustration now will give things much clearer. So if this is the surface, and if I'm walking on this surface, say for example, my points are walking on this path are marked by this. Now if I take a kind of a curved surface like this, and the same way if I start walking from here to here and to here, what happens is that you see this curved surface, if I take a chunk out of the sphere, that locally resembles Euclidean space near each point. That means Euclidean means general, just like a table, chair, our office, etc. So it locally looks like this. I mean to say, so this is the global structure and this is the local structure. This is what is differential geometry on a very gross level, and this is why differential geometry is used, because we need to identify and measure those complex curvature of structure, because Earth is not flat, it is curved. So you see, it started basically with Riemann, and in his the thesis paper which he was submitted for his doctorate at Göttingen University. This was the paper on the hypothesis which lies. So fundamental to general relativity, it was later studied by Grossman and others and incorporated by Einstein in general relativity, and the study of Riemannian manifolds started using what is called a Riemannian metric. So if you really want to take a kind of a quick look about the development of differential geometry. So differential means we are going to differentiate what? The geometry, so that we can apply calculus. As simple as that. So this actually shows a very important branch of mathematics which we are still studying, and I've got a separate set of playlists which deals with the mathematics of differential geometry. Anyway, so we now understood why differential geometry is important and what it does. It differentiates the surfaces, and we apply calculus to measure them. The question arises still that why do we use tensors? What at all tensors are useful and why they are useful for that? So you see that tensors look something like this. This is the metric tensor which measures the causality of structure of spacetime. This is the stress energy momentum structure. So we can say that the tensors actually calculates the stretching factor. That means how much the space is stretched. Okay, it allows for the path length and proper length to be calculated. It replaces Newtonian gravitational field. Let us forget the second part. It's too technical. It determines the shortest path between two different points. Yes, it is important, and we will soon into this. But can we see a little bit more into what those components T00 actually tells about? This is a typical example of a stress energy momentum tensor. So everything related to energy, you can find it over here. So the momentum density comprises of this part. Momentum density comprises of this part. Energy density is the red one. This is the shear stress. This is the pressure. And this is the momentum flux. So what do we mean by that? That means this particular house, this particular brick-like structure, whatever you see, the tensor actually is a codified version of everything which is under one roof. And that is basically the role of tensor. So here you see E equals to mc squared. So the energy, that is the speed of light, will always be at the top, T00 marked as red. Because of the speed of light, the energy density will always be at the top. So we can say every part of energy that we can think, maybe pure energy, rest mass, stress, momentum, relativistic momentum, everything is being stored over here. And that is how the tensors really work for. Now the next question arises is that we just talked that it measures the shortest path. Right, so what is that? So this is a summary. Let us understand. A tensor is always same in all coordinates. The components of a tensor may be different in different coordinates. An equation involving only tensor quantities is the same in all coordinate system. So these are some of the important points of tensor, because if you ask that what a tensor does, so we need to create a mathematical model so that we can predict the change of event in space-time, either in contravariant manner or in covariant. We are not dealing with this. This is something specific to tensors. Contra means opposite. It should be either opposite or in the covariant. That means it should move along with that. So here is a summary. Tensors will help us understanding transformational properties. Why transformational properties? Because we are moving from flat space to curved space. Always the same in every coordinate system. Obviously, otherwise how will we measure it? And whose components do transform, as you have seen that the components of the vector sometimes stretches, sometimes shrinks, but in a nice way. That means in a predictable manner which we can predict for. Okay, now we come to another very important concept, I would say, not a technical term, but a concept which is called geodesics. Now, geodesics are basically something which are called the shortest path that a particle travels. Here it passes in a straight line. Here also it passes in a straight line. But in a curved space, something like this, it would travel in a curvature. So like this, it will also travel with these two black points in a curvature. So given a tram, if you ask that where will the tram move, in general you can say that given the initial position and the second order derivative, you can calculate the speed, velocity, etc. But if you ask a general relativist, it would say this is the path of the tram and this is how it is going to move. So the tram would take a path which is quite straight, and it will take the path which is right in front of it. So it says that geodesics are nothing but simply these are the shortest path between 2 points. So let us see a little bit more. So geodesics are these we name. So it generalizes the notion of a straight line to a curved space, because that straight line doesn't remain straight anymore. It becomes curved. And you see that gravity is due to the curved space-time. This is the source of stress energy momentum tensor. And you can say that an object moves through space-time in a straight line. But if the space-time is curved, That means the gravity is obviously present and may change direction like you are moving in a surface of a sphere. Now we just understood that geodesics are the shortest path between these two, between space-time, between any two surfaces. It can be straight or curved. Now the question arises that we are talking of general relativity, etc., but how does the measurement actually happens? I mean to say, what does the role of Einstein's relativity plays? So this effect is what we call gravity, and now we will see a little bit about what actually is the measurement and the core idea of Einstein's field equations. So here you see this, it is a set of 16 equations. This one actually are the dimensions is space-time. So it is 1, 2, 3, 4. This one's mu nu is also a space-time. So again 4. This one is also space-time and again 4. And this is also the dimensions is space-time, again 4. So 4 plus 4 plus 4 makes it 16 in total. And mu nu are the indices measuring space-time. So I have been telling you 16 equations, etc. So right now I have shown you that the dimensions that these things measure are called makes a total to 16 equations. The questions are those which I have marked in red. What actually are the equations? Let us find it out in a very simple term. The first R is called the Ricci curvature tensor, which is named after the famous Italian mathematician Gregorio Ricci Curvastro. And what it does, it measures the volume of a matter when it changes from flat space to curved space. The next R is basically called Ricci scalar, and it keeps the track if the size of a ball when it moves from Euclidean space to curved space, how the size of the ball actually deviates. The next one, that is this small g which occurs twice, is called the metric tensor, very important way of measuring distances of all the causal structure of space-time. Next comes the Riemann curvature tensor, which is little bit hidden. I will tell you later why it is hidden. And the next comes, so this is hidden, and this T is called the stress energy momentum tensor, that is the matter movement through space-time, which I told you, momentum, density, flux, etc. Now all these 1, 2, 3, 4 and 5, if you really want to know each of those tensors, what they are about, how they come and what are their role, go back to my playlist in General Theory of Relativity. All these are given in much details. Each of these has a separate video, and the metric tensor is quite a long video, but it contains each and every details. So you want to know, you can go back and check on those components later into my playlist. Right. So the other thing that we get, this lambda is a cosmological constant. This is the speed of light. The 8 pi is also a constant, and g is Newton's gravitational constant. Now what actually all those equations tell? Right. So these are all constants. Let us see that what actually it leads to. So what we see is that this equation, this entire left hand side measures the curvature of space-time, right? And the right hand side, and it is the geometry of space-time. This right hand side actually tells the matter energy content of space-time. That means how much matter is present, how things are moving. And this is the matter movement. Both of them are equated with an equal to sign. And what it tells is this. Simple. Space-time tells matter how to move, and matter tells space-time how to curve. Right. So this is ultimately it boils down to this single part, that the left-hand side measures the curvature of space-time, the geometry, and we just saw how the curvature is measured through differential geometry, tensors, etc. And the right-hand side, this T mu nu primarily is the matter energy content, which tells how matter moves. And this geometry of space-time is equal to matter movement. Simplified in the line at the bottom, space-time tells matter how to move, and matter tells space-time how to curve. Okay, now we got to the core idea of general theory of relativity. More or less, there are certain implications. I mean to say, because of general relativity, we could see a lot of things. Let us see what are those. First of all, it affects the path of light. So there is I've got a video which says that the mass of a photon is 0, then how does the gravity affects? You can watch that video later. So first of all, we need to find out how gravity affects the path of a light. So what we see here, you see Jupiter, Earth and Mercury given, and this is the curvature of Jupiter is higher. So you see the dent is more, the curvature is more because the weight is more. If you see Earth comparative to Jupiter, it has got a lesser dent, this red one, and that is why the G and I would say the weight is much less. Mercury comparatively is even lesser, that is why the red dent is low, and that is why the curvature is even less, and the weight and the G. So you see that these planets are being now shown, or I would say depicted, in terms of the curvature. So higher the curvature, we can say that the gravitation and acceleration G as well as the weight changes. So, and we know that tensors measure curvature. Okay, now we come to the thing. So if I take 2 points and throw a photon or a streak of light, so you see that in the absence of mass, the photon travels in a straight line. But I give here a sun which has got quite a heavy mass, and if I throw the light, it is going to go here, and you can see here. It's a nice animation. I think you can just watch it again. So here it comes the light, and it then bends down, goes a little bit up and comes here. So what I'm trying to tell is that the photon takes the path of the geodesic that appears curved. Remember that tram which I have explained you. So what does the tram move? It doesn't move. It actually moves straight, isn't it? The tram is actually moving straight. Here also the light is moving straight. It is not moving anywhere else. But while moving straight, it is exactly taking the path, the curvature as given by the space-time curvature. So the curvature is due to the presence of mass, and here gravity is the bending of space-time due to matter, and that is why you see the apparent movement of the photon. So a nice demonstration which was first done by Sir Frank Watson Dyson and then by the famous Arthur Eddington. They went for an expedition which was on 29th of May 1919, and the Earth and the Sun and the light was straight. This is the actual location of the star, but due to the presence of and it should have measured here, right? Apparent location of the star. Due to this, there was an angle which is called the Einstein angle, which he later corrected 1.75 arc seconds. And that is why it's the first time that this proved, the total solar eclipse actually proved that the bending of light is due to the presence of curvature. It's famous done by, it is when, I think it's the island is Hawaii, or I just forgot. So you can let me know where the experiment took place in the comment section. So Arthur Eddington and Frank Watson Dyson first noticed that the apparent location changes. Nothing that the star has moved, but due to the sun, the photon takes a different path, and that is due to the presence of curvature space-time. Now, this delta is basically the deflection is of a very small angle. So the 1919 solar eclipse can be seen like this. So the Newton's angle was something 0.88, which was corrected by Einstein's angle, and this is the famous cutting from that newspaper during that time which came up. And although it was first done by George von Soldner, and then it was further proved by Eddington. So here is a summary. The bending of light around massive objects is now known as gravitational lensing and has become an important tool in astrophysics. And physicists now use gravitational lensing to expand or understand something which is called a dark matter. So Sir Arthur Eddington was extremely happy, and all the world, we were all happy that ultimately Einstein's general theory of relativity has been proved experimentally. And during those happy moments, this is the poem which he wrote. Oh, live the wise hour measured to collate. One thing at least is certain, light has weight. One thing is certain and the rest debate. Light rays when near the sun do not go straight. And this was a kind of an Rubaiyat style which he wrote at the Royal Astronomical Society during the dinner. So this is one of the most important event, a breakthrough in the history of science, how Eddington's and the solar eclipse experimentally proved, not mathematically, that Einstein's general theory of relativity is correct. Now, apart from this, there is one important concept which is still we are probing deep into and understanding, that is the concept of black holes. Now, there is a concept that does time stops near a black hole. what actually it happens. Let us look into this part of the video. So as we have seen that Jupiter, Earth, and this actually is the curvature. So if we take a kind of a structure which is like this, so we know that matter causes space-time curvature. So it is a region, black hole, where the gravity is so intense that light ray cannot escape. So you see the curvature goes deep down, right? And this is where the curvature is the highest. And that is why you see the deflection of the light cannot come out of that hole. So that is why we cannot see, and light rays cannot escape, and that is why we call it as a black hole. Now the thing is that if we take the Einstein field equation and see, then this part we know is actually how space-time is curved, and this is the matter content which causes the curvature. So you see here the curvature, and we know that it is the deepest. Now if you plot this kind of a figure, right, the sun and white dwarf is more it has got more mass, so more curvature, and neutron star, then what we will see is that, see, neutron star has the heaviest, the length is less. White dwarf, the length is even less, and here the black hole has got a length is more. We will come to this point why I'm showing this. So when we look into this flat kind of a surface, and then we move into something which is kind of a curved surface, right, and we have got the sun, neutron star, and black hole. So you see what happens is that neutron star has a less curvature, black hole has the highest curvature, and if we plot this curvature, I'm going to say just a space and time, x and y axis, then what we get is this, right? You see that the curvature is, the time is in here, and the space moves from here. So the time taken is more than the flat space, because in flat space you can see right on the left hand side corner of your screen, it is a straight line. So straight line will just zip through. Whereas if it is a curved space, that means the time is taken will be more. So time, we can say, slows down near a black hole with an extremely strong gravitational field of the black hole. My main purpose is basically to bust the myth that time really stops. No, it doesn't stop. Time goes on ticking. If you see a clock, if you go into my other videos in black hole, I've explained this in much more details. Why time does time stops, and everything about black holes, the creation, etc. So time doesn't stop. Time goes on ticking, but the curvature takes a little bit more time. As you can see, the black hole has got more curvature than that of a neutron star. So here is a nice analogy which I would like to show. This person is over here, and it travels deep down up this point, and it reaches over here, and we take what is called a Schwarzschild black hole, and he starts at 9 a.m. and he goes down the black hole somehow like this. So it is taking more time, right? And it reaches over here around 3 p.m. right? Straight. Now if I take the surface of Earth, and if I take this person who starts at 9 a.m. and you will see if you take the curvature is even lesser, he reaches around 11 a.m. right? So the time taken for a person traveling in Earth is just 2 hours. Right? Whereas the time taken for the person traveling the Schwarzschild black hole, or in general a black hole, is 9 to 10, 10 to 11, 11 to 1, 11 to 2, almost 4.5, 5 hours. So this is the essence. This is what is called the time actually stops near the black hole. It doesn't stop here. It actually travels, and the curvature makes it appear that it stops. So this is all in all what I wanted to tell you. That is, this is a kind of a general journey of simplified version of Einstein's relativity. So the time slows down because of the curvature. So the time we need to mention is just a coordinate system in general theory of relativity, and because the coordinate is curved, so it takes more time. A simplified version of Einstein's general theory of relativity. So we can say finally that would you age slower near a black hole? A person near a black hole which will age slower because the passing of time is slowed down due to the extremely strong gravitational field and the curvature that it takes. When we talk about time dilation and time slowing down, we are talking of the physical process. The passing of time can fundamentally only be observed by things changing, and yes, being near a black hole does affect aging. So this is actually the fact, the actual mathematics, the actual physics, that would you age slower near a black hole, how it happens, and this is how it happens. So I hope you like this video. I know it has taken a lot of time. It is a lengthy video, but it is a complete journey without much into mathematics complex details. How general theory of relativity evolved, who are the contributors, what are the main ideas of general relativity, field equations, differential geometry, and so on. I am very, very thankful to you for taking all the patience of watching. Please do subscribe to my channel and help me to grow. Click on the bell icon and click on all to get all the notification from Physics for Students. And if you really want to contact me, because I reply to the mails asking questions, mathematical physics concept, you can write to me. This is my email ID. Also to mention that I've got a separate channel which is still under a growing stage, which is called this one, General Relativity Explained, which I am keeping it only and exclusively for the physics mathematics of general relativity. I've put on few videos, not getting enough time. You can watch it. And if you want further, you can follow me at my Facebook profile, at my LinkedIn profile, and my Instagram profile. Thank you very much for watching this video. I hope you liked it. Please do let me know in the comment section, how did you like a simplified approach to general theory of relativity? Stay tuned at Physics for Students, because I will be back with more interesting and even more fascinating videos. Till then, goodbye and do take care.